So if we're given this implicitly defined equation and we want to find dy dx, we have to take the derivative of both sides of it with respect to x, because we're looking for dy dx, which means the derivative with respect to x. So we're going to take the derivative on both sides with respect to x. So on the right side of the equal sign, it should be pretty easy. Right? Derivative of 5x is just 5, and the derivative of 1 is 0. Good with that? Hopefully. Okay. So what about x squared y? Well, x squared y is x squared times y. Those are two separate functions. So when you take the derivative of x squared y, you have to use the product rule. So that will be the first function, x squared, times the derivative of the second function. So the derivative of y with respect to x is dy dx. Anytime you take the derivative of a y term, when you're doing it with respect to x, you have to attach this term of dy dx to it. Some teachers teach it as like they attach a y prime to it also, but instead of a dy dx, but it's the same thing. So that's first function, x squared, times derivative of second function, y. And then we need to do plus derivative of first function, 2x, times second function, y. And this time, since we didn't take the derivative of the y, it was just the y when we did the product rule part of it, multiplying by the original second function. It just stays as a y. Good with that so far?
Yeah.
Okay. And then our 3x cubed just becomes a 9x squared. And then the 2y, or sorry, the y squared becomes a minus 2y. But since we're taking the derivative of a y term, it has to have a dy dx attached to it. Good or no? So far?
Yeah.
All right, so now we just want to solve for dy dx. So in order to do that, we'll gather all the dy dx terms on one side, which is the x squared and the minus 2y, and factor out the dy dx from them. And we'll put everything else on the other side. So 5 and then minus 2xy and then minus 9x squared. And so then we just divide and get 5 minus 2xy minus 9x squared over x squared minus 2y. Good or no?
Yeah, thank you.
No problem. Any other questions on anything that we have done in the past? All right, give me 1 second. I gotta go take care of something real quick. I'll be back in like 2 minutes. Sorry, be right there. Okay, sorry about that, everybody. Had to take care of, but we're good now. Any other questions from any of those assignments, or just in general, anything we've done that you're not sure about this year?
Just to clarify, for logarithmic differentiation,
Uh-huh.
you always multiply both sides by ln, right?
We're not multiplying by ln, but you always take the natural log of both sides.
Okay, yeah. Okay, thank you.
Mm-hmm. Any other questions?
Can you go over like a basic logarithmic differentiation problem?
Sure. You want to just pick one off of that worksheet, or
Yeah, sure.
I can also just make one up if.
Either way, I just want to remember the process.
Okay, sure. I'll just make one up. So something like y equals, let's say, sine of x to the power of cosine x. So it's a function being raised to the power of another function. So we take the natural log of both sides. And since now I'm taking the logarithm of something to a power, I can pull the power out to the front. So we end up with natural log y equals cosine x, first function, and then second function, natural log sine x. Does that make sense so far?
Yeah.
Okay. And then now we take the derivative with respect to x of both sides using implicit differentiation. So 1 over y dy dx. And then this one is a product rule, so it's cosine x. Then the derivative of natural log sine, so 1 over sine times the derivative of sine, which is cosine. And then plus derivative of cosine, which is negative sine, times natural log of sine. And from there, we then multiply both sides by y, right? And since y is sine x to the cosine x, we end up with dy dx as y, or sine x to the cosine x. And then times, that becomes cosine squared over sine minus sine x natural log sine x. Does that make sense and help?
Yeah, thank you.
Mm-hmm. Any other questions?
Where did the cos x come from in the second to last line? Like where it's cos x times cos x over sine x?
Which cosine are you asking about?
The one in the parentheses.
This one in the numerator here.
Yeah.
So this is the product rule. So it's the first function cosine times the derivative of natural log of sine x. The derivative of natural log of sine x, that's natural log of u with u equal to sine x, right? It's a composition of one function inside of another. So it's 1 over u times the derivative of u, and the derivative of u is the derivative of sine, which is cosine.
Okay, got it. Thanks.
1 over sine times cosine. Any other questions on that? Anybody? Or on anything that we've done so far this year? All right, let's move on then to what we're going to talk about today, which is the last little rule for taking derivatives. And this rule only applies to two functions that are inverses of each other, right? So hopefully you're familiar with what inverse functions are. It should be something you've learned in the past. What are some things you can tell me about inverse functions? Just in general, without reading any of this and without looking something up. What can you tell me about inverse functions?
They're a reflection of each other over y equals x.
All right, the reflection over the line y equals x. That's the first and most important thing, the reflections over y equals x. And that's very important because it tells you that for any y value on one, it's an x value on the other, or for any x value on the other one, it's a y value on the other one. For example, if, let's say, the function f of x has a point on it that is 1, 2, what would f inverse have on it? What point would it have?
It would have 2, 1.
There we go. It would have 2, 1, right? If f has 1, 2, then f inverse will have 2, 1. And last thing, what is f composed of f inverse of x?
Isn't it just x?
It's just x. And the same with f inverse composed of f is also x. All right, sorry about that. So this is the basic information that you should already know about inverses. And so what we've got here is we've got two different functions which are inverses of each other, right? Here's the original function, f of x, and here's our inverse function. And we'll note that f of x has a point on it that is b, a, and f inverse has a point on it that's a, b. So when we are looking for derivatives of the inverse of a function, what we need to do is we need to find these points that they don't share, but they have these sort of common points, a, b, and b, a. And if we can find those, the slope of the inverse function, right, the derivative of the inverse function at a, should be equal to the inverse or the reciprocal of the derivative of the inverse of that function at b. So sometimes this is kind of how most textbooks formally state it, but I think it's a little easier if f and g, we'll call it f and g, are inverses, with f having a, b, and g having b, a, then f prime of a is 1 over g prime of b. That's all it's saying, that the derivative of f at a is equal to its inverse's derivative at b in the denominator, right? 1 over that. And that should sort of make sense, I hope, because, how do we find slope? Well, slope is just a change in y over a change in x, right? And so our slope here ought to be our change in y, which is the b, over the change in x, which is the a. And here it should be the a over the b, which should just be flipped around. It should just be a reciprocal. Does that make sense? Or no?
Yes.
Cool. So we're going to do a couple of these, and then I'm going to set you free to practice some on your own. So we've got f of x is x cubed, and g of x is the inverse of f. We want to know g prime of 3. So we're going to do this one two different ways. One is using the rule, and then we'll do another one after that. So we need to first concern ourselves with the sort of shared, it's not a shared point, but this like common point that's the point of interest here. G, we know, since we're looking for G prime of 8, must have a point where the X value is
8.
8, which tells us that F must have a point where, what?
The y value is 8.
Where the Y value is 8. And G prime of 8, according to this rule, ought to be 1 over F prime of whatever value this is, right? Question is, what is that value? Well, if F has a Y value of 8, that means that F of X, which is X cubed, needs to equal 8. And if we just solve that equation, it should tell us that that's true when X is 2. And that tells us that the Y value of G there is also 2. Does that make sense how we found that?
Yes.
Or, yeah, okay. Any questions on that? Everybody okay with that? All right. So all we need to do then is figure out what's F prime of 2. Well, what's F prime of X? What's the derivative of F of X?
3x squared.
3x squared. And if we evaluate that at 2, what do we get? We get 3 times 2 squared, or 12. So that tells us that G prime of 8 ought to just be 1 over 12. Good or no?
How do we tell the difference between when the prime means derivative or when it means inverse?
The prime will never mean inverse. This is what's telling us that the functions are inverses of each other. G of X equals F inverse of X there. But the prime will always mean derivative. It never means inverse. Good or no?
Yeah, I just forgot about the negative one. But
Ah, okay. Gotcha. Yeah. All right, so real quickly, we could have said, well, here's F of X is X cubed, right? And G of X is the inverse. Well, how do we find the inverse of X cubed? We could have just found the inverse function, right? How do we do that?
You just solve for X.
Yeah, you just solve for X, right? And it gives you cube root of Y is X, and then you exchange the values. So G of X would be X to the 1/3, right? Cube root of X. So we could have found G prime of 8 just by finding G prime of X, 1/3 X to the negative 2/3, and then plugged in 8, 1/3 of 8 to the negative 2/3. And what's 8 to the negative 2/3? Well, that's 8 to the 2/3 in the denominator. And 8 to the 2/3, well, cube root the 8 is 2 and squared is 4. So this is 1 over 12, which is exactly what we got. So we could have not used the inverse rule, and we could have just found the inverse of the function and then plugged in, right, which would be fine. But there are cases where it's not very easy to find the inverse function of what we're dealing. So we were dealing with a pretty straightforward function there, X cubed. But suppose I gave you something like F of X equals e to the X plus X. Well, solving that for X is going to be a little bit more problematic. So let's see if we can get this one worked out. Any thoughts on how we're going to start this? What do we know about G?
The x value is 1.
Has an x value of 1, which tells us what about f? It should have a common point there, or a related point where
The
Y
y
value.
values.
yeah, the y value is 1. So now we just need to figure out when that's true. So when does f of x, e to the x plus x, equal 1? And while that's not an easy equation to algebraically solve, it's one that if you plug in a couple of basic numbers, you should be able to figure out what x value works for that. What x value makes that true?
0.
Yeah, x equals 0, right? Because e to the 0 is 1 plus 0 gives you 1. So x equals 0, which means the y value there at g is 0. And if we want g prime of 1, it ought to be 1 over f prime of 0. And what's f prime of x?
E to the x plus 1.
Yep, e to the x plus 1. And so if we evaluate that at x equals 0, what does that become?
2.
2. And so g prime of 1, which is 1 over f prime of 0, is 1 over 2. Easy enough or no?
Good.
Excellent. All right, that's it. That's all we're doing today. Nice, short, easy day to get us back from Thanksgiving break here. Don't worry, tomorrow won't be so nice, short, and easy. Anybody have any questions on that?